What the fuck?
Hey everyone, welcome back and let's write some more neat code today. So today let's solve linked list cycle. I know that we solved a problem that's pretty much a harder version of this exact problem, but in this explanation I'm going to explain why the tortoise and hare algorithm on a linked list cycle, why exactly it works and why exactly we know for sure that it's a linear time algorithm, because I think most people just kind of glance over why exactly this is true. So I'm going to go over that today. And you can see that this linked list problem is another problem from the blind 75 list, a list of 75 problems we've been working through and tracking on this spreadsheet. The link to the spreadsheet will be in the description if you want to take a look. We are not quite done with this sheet yet, even though we have done pretty much most of the difficult, medium, and hard problems on this list. So basically, we're given the head of a linked list, and we just want to determine if there exists a cycle in this linked list or not. And basically, the definition of a cycle is if at some point, you get to a node and you keep following the pointers along that node, eventually you'll get back to the same node. And if we get back to the same node, we'll be able to do it again and again and again, basically an infinite loop. So we return true if there's a cycle, we return false if there's no cycle. Now, the first idea you might have is just start at the beginning, keep going to the end, keep going, keep going, and eventually, let's say that this -4 actually pointed to null. In that case, we know, okay, we got to the end of a linked list, right? So in that case, we return false, no cycle. And that's always going to be the case. So if there's no cycle, it's really easy to detect that there's no cycle because eventually we reach null. But if we don't reach null, right, we go along this node and we get back to the same node we already visited, but for some reason we can't detect that. So then we go to the next node, and keep doing that. And from our perspective, we're just going to say, okay, it's just a really long linked list. Eventually we're going to get to null, right? But that's not going to be the case. If there's a cycle, we never get to null. We'll never break out of this loop. So we really have to determine a way to detect that we're visiting the same node twice. So how can we determine if we're visiting the same node twice? Well, we start at the beginning like usual, and we maintain a hash map or a hash set in this case, where basically we take every single node and we take the node itself and add it to the hash set after we have visited this node. We don't add the value because I think in this problem there could be duplicates, right? Like the same value could show up multiple times in multiple nodes. So we don't want to detect a loop that way, but we'll take the node itself and then add it to the hash set. And I think you can do that in most most languages. You definitely can in Python, because the node itself is just an object and you usually can hash an object. And so in that case, we're going to take this, visit it, take this, visit it, take this, visit it, take this, visit it, and then eventually we'll get back to a node. If we notice that a node has already been visited and now we're visiting it twice, that obviously means that there must be a cycle, right? We can't visit the same node twice. So that means there's a cycle, we detect that, and then we can return true, a cycle exists. Now in this case, we're only having to visit each node about once, so the time complexity is going to be big O of n. The memory complexity is also going to be big O of n, because every node potentially is going to be stored in the hash set. But there's actually a way that we can do this without using a hash set. We can do this in O of 1 memory, and that's the slightly complicated algorithm. I'm going to show you that algorithm, and I'm going to show you exactly why it works. So the idea is simple. We're going to start at the beginning of the linked list, but we're going to have two pointers this time. We're going to have a slow pointer S, and we're going to have a fast pointer F. And you may have seen this algorithm before. It's a pretty simple algorithm once you know it, but I'm going to again show you why exactly it works. So the slow pointer each time is just going to be shifted by 1. The fast pointer is going to be shifted by 2. So it's going to be here. And so originally they do start at the same position, but we're going to look at every position after we've shifted it. And so what's either going to happen, obviously the fast pointer is faster than the slow pointer. So if there is the end of a linked list, right? Like for example, this points at null, the fast pointer is of course gonna reach the end of the linked list first. So if we do that, then we can return false, no cycle exists in the linked list. But if there is a cycle, do you see that this fast pointer and this slow pointer are going to meet again? They're going to meet at the exact same position. And if they meet at the exact same position, that must mean that a cycle exists. So I'm just going to run the simulation, and then I'm going to show you why it's always going to be the case that these two are going to meet if they ever reach a cycle. So we just take one more step with S, right? We're only shifting it by 1. F is going to be shifted by 2. So first we're going to go to 4, and then we're going to follow the link and reach back to this position, right? The 2 position. So clearly F made a loop. F has gone through the cycle. And so far we've shifted each of the pointers twice. And so we're going to do one last shift. S is going to reach the 4. And our F from over here is going to be shifted twice again, and it's going to reach the 4 as well. So at this point, we're going to see, yes, the slow pointer and the fast pointer have met each other. How could it be possible that they met each other if the fast pointer was going twice as fast? Because they were in a cycle, and eventually the fast pointer, no matter where they start, slow is here, fast is here, eventually the fast pointer is going to catch up to the slow pointer. Let me show you why that's always going to be the case and why it's going to happen in linear time. So let's say this is our cycle, and I'm not drawing it as a linked list. It's some kind of circle, right? And it's a cycle. And let's say we're moving clockwise in this cycle. First thing to notice is, do you know that every gap, so let's say, the distance between slow and fast, that's going to be some integer value, right? It's not going to be a decimal, it's going to be an integer value. And this portion is also going to be an integer value because the entire length of the cycle is going to be an integer value because, linked list lengths are integer values, right? This is an integer 1, this is an integer 2, also 1, so the entire list is length 2, right? So we're dealing with integers here, not decimals. So we're looking at the case where the slow and fast pointer are at different positions, because obviously if they were already at the same position, we're inside the cycle, they're at the same position, then of course we know we're going to return true. But it could be possible that they're at different positions. Any arbitrary position is what I'm choosing here. And we know that the slow pointer on one iteration is going to make one jump, right? The distance it's going to move is 1. We know that the fast pointer is going to move a distance of 2, right? So clearly, in our simulation, eventually the fast pointer is going to reach and surpass the slow pointer. But why is it true that they are going to meet each other at the exact same spot? Well, let's just give this distance an arbitrary value. We know that the fast pointer will catch up to the slow pointer, and this is the distance that it's going to have to travel in order to do so. This is our gap that we have to close. So let's say the length of this gap is 10. If we move the slow pointer by 1, we're taking the gap and increasing it by 1, right? If the slow pointer gets shifted by 1, we increased the gap. But then the fast pointer is not going to quit. It's going to move by 2 as well. So when we move the fast pointer, we're taking the gap and closing it by 2. So we're saying plus 1 minus 2, right? Do you see how this evaluates to 10 minus 1, which is going to be 9. So on a single iteration of the loop, the distance between the pointers is being closed by 1. So then how many iterations is it going to take for the fast pointer to reach the slow pointer? Well, of course, whatever this length happens to be, right? Whatever that closing distance happens to be, whatever that gap happens to be. How big could this gap possibly be? It could only be the entire length of the list. So, let's say the fast pointer is over here where this distance is 1. So then the remaining distance is going to be the entire length of the list. Let's call that n minus 1. So then how many iterations is it going to take to get this to equal to 0? Of course, roughly n. So that's why the overall time complexity is n, where the length is the distance, where n is the length of the cycle, which could be the entire linked list, right? So that's why it's always going to work, and it's going to run in linear time. And maybe you didn't even care about why exactly it works, but that's okay, because once you know the fast and slow pointer technique, the code is usually pretty easy to write. Let's get into that now. So like I said, we're going to start our slow and fast pointer at the same position, and the next time that they meet each other is how we know we've detected a loop. So obviously they're at the same position now, and we're going to be shift to say that there already exists a loop, because we don't know that for sure, and we're going to be shifting our fast and slow pointers while fast and fast.next is not null, because we need to make sure that fast.next is not null, because remember, we're shifting fast by 2 on each iteration. And of course is not null, because remember, we're shifting fast by 2 on each iteration. And of course, fast is going to reach the end of the linked list before slow does. So if it does that, then outside of the loop, we can return false, meaning that there does not exist a cycle. But on the inside, we're going to check if there is a cycle. So we're going to take our slow pointer, shift it by 1, slow.next, take our fast pointer, shift it by 2, fast.next, next again. And now if they meet each other, we can say if slow ever reaches fast, then we can return true, there does exist a cycle. And you could pretty much write this loop as a do-while loop in a lot of other languages, but I don't think Python supports that. So the solution is really as simple as that: linear time, constant space. You can see that the solution works and is efficient, so I hope this was helpful. If it was, please like and subscribe. It supports the channel a lot.
toi, prie-moi, répète-toi, mémoire.